We're now going to take a look at an equation and use the mean value theorem, or rather one of its corollaries, to figure out the number of solutions. So we won't figure out exactly what the solutions are, but just a number. So let's see how to do this. So the example we're going to take a look at is x to the square minus 2 to the x divided by x to the squared plus 2 to the x equals 0. And the corollary of the mean value theorem is this: f prime bigger than 0 on an interval means f is increasing on that interval, and f prime less than 0 on an interval means that f is decreasing there. And we'll also use the intermediate value theorem, which says that if f of a and f of b have opposite signs, you can actually write this as saying that the product is negative. So this is only true if they have opposite signs. And f continuous on AB. This implies that there exists a point C in AB such that f of C is equal to 0. Now, of course, this implies that there exists at least such a C. So we don't know that there exists exactly one point here, which is a problem. So this can give us a lower bound for the number of zeros of a function on various intervals. And the point is that this can give us an upper bound, okay? Because where you're increasing, strictly increasing, I should write here, you can only have one zero, or strictly decreasing. So let's look at how to do this. So of course, to use this corollary or the intermediate value theorem, we have to make this into a question about a function. And gee whiz, this is a function. So let's call him f of x. And to apply all of this business, we can first notice that this function here has domain all of R. And since on all of R, it's a combination of polynomials and exponential functions, it has to be continuous there and differentiable. Now, what is f prime? So f prime, to compute him, let's first notice that 2 to the x is equal to, well, 2 is equal to e ln 2. Then exponentiate with x, so I get e to the x ln 2. So when I want to differentiate this guy here, so compute his derivative, I can use, so let's here take the derivative like this. I can use the chain rule. So the inner derivative will be the derivative of this thing with respect to x, that's ln 2. And the outer derivative is the derivative of e to the whatever with respect to whatever. And that gives me just e to the whatever. So the exponential function does not change under differentiation. So, and then 2 to the x. So when I now differentiate this, I first use the quotient rule, meaning I differentiate this thing and keep this thing. That would be 2x minus ln 2 times 2 to the x. I multiply this with the guy downstairs. Then I have to subtract the derivative of this guy multiplied with that guy. So it's 2x plus ln 2, 2 to the x, and then x squared minus 2x like this. And downstairs I get x squared plus 2 to the x squared. And now I multiply out and simplify. So I multiply this in here, so I get 2 to the x third, and then I get plus 2x times 2 to the x. And now I get minus ln 2, 2 to the x squared. So this thing multiplied together, and then I get this with this, which is minus ln 2 times 2 to the x with a square like this. Now I subtract all of this, so that's minus 2x to the third plus 2x times 2 to the x minus ln 2 times 2 to the x times x squared, and plus ln 2, 2 to the x squared. And then all of this is divided by x squared plus 2 to the x squared. This cancels against this, and this cancels against this. So what's left? Well, this and this doubles up, and this doubles up. So I get 4x 2 to the x minus 2 ln 2, 2 to the x squared divided by, well, the same thing as always. And now, of course, I want to study the sign of this guy, so where he's positive and negative. So I need to factorize this as well as I can. So let's move what's common here outside of a parenthesis. So I can move 2x and 2 to the x. What's left here is just the number 2. And what's left here is ln 2 times x. And all of this, of course, over this factor that I don't really care about since it's non-zero and positive everywhere. So let's now make a table of signs for the derivative. So let's do a real line like this. Who are the factors here determining the sign? Well, it's x, and it's 2 minus ln 2 times x. This guy is 0 here, and this guy is 0 at, well, I don't know exactly the value of that number, but it's 2 divided by ln 2. So this is negative, 0, and positive. And this guy here is, if x is larger than positive, this dominates. So he is negative here until he's 0 there, and then he's positive, like this. And all in all, this means that f prime is negative here, 0 here, positive here, 0 here, and negative here. Now I use this corollary of the mean value theorem. So I translate this into information on f, saying that I'm decaying here, increasing here, and decaying here. So if I now want to know the number of zeros of this guy here, I can see that since I'm strictly monotone here, I have at most one solution to the equation f is equal to 0. Here I have at most one solution, and here I have at most one solution. And now we want to use the intermediate value theorem to say that I have at least one solution on these intervals, or I want to know that I have 0 solutions on these intervals. How can I determine this? Well, I need to figure out what's my value here, what's my value here, what's my limit here, and what's my limit here. So I have 4 question marks to fill out. So how to do this? Well, let's do the limits first. So let's do limit x goes to minus infinity first, like this. Let's recall who f of x was. So f of x was x squared minus 2 to the x divided by x squared plus 2 to the x. And when x goes to minus infinity, these two guys go to plus infinity. And here I get this to the minus infinity. So this guy here goes to 0, and this guy goes to 0. So here, if I want to do it strictly by the book, I'll factor out these two terms since they are the strongest. They'll kill each other. I'll get a 1 here, a 1 here, and then a term here and here that will go to 0. So let me not do all of that, but let's just say that in the limit, this tends towards 1. So this question mark here is a 1. And I don't really care that the value is 1. All I care is that it's positive. So now let's figure out what happens when I go to plus infinity. So I'm having the same expression here. Again, these two go to infinity, but now these two guys also go to infinity. But now these are the strongest, right? Exponential growth into infinity. So if I'm to do this by the book, I'll factor out 2 to the x above and below. They'll kill each other. Here, the terms I'm getting will be x to the square divided by 2 to the x. So this term will go to 0, and this will go to 0. In here, I'll have a 1 and a 1. So all in all, this will go towards minus 1 divided by 1. So this goes towards minus 1. So this question mark here is also handled now. And again, I just care about the sign. Now, what about these two question marks? Well, let's figure out this one. So f at 0 is equal to what? Well, it's 0 to the square minus 1, and 0 to the square plus 1. So I'm getting here minus 1. So my value here is minus 1. And notice, since I'm moving from plus 1 to minus 1, I can use the intermediate value theorem here to say that I must have at least one solution for the negative x. So at most one solution, and then from the intermediate value theorem, at least one solution. So here I have exactly one solution on this interval here. So now, notice if this now is a positive value, then both here and here I'll get at least a solution. So all in all, I have 3 solutions. But if this is a negative value, I'll get no solutions here since I'm going from negative to negative to negative. Or if this is exactly 0, I'll have one solution on this entire thing here. So it's still possible for me to have 1, 2, or 3 solutions. So to figure out which is which, we need to plug in here 2 divided by ln 2, which gives me what? It gives me 4 divided by ln 2 to the squared minus 2 divided by ln 2, and then here 4 ln 2 to the squared plus 2 ln 2 divided by ln 2, like this. And here, well, this isn't going to be something nice, but let's just notice that 2 to the power 2 ln 2 can be simplified somewhat. So 2 is e to the ln 2. This I take to the power 2 divided by ln 2, so this cancels against this. So I get e to the squared here. So here I have 4 divided by ln 2 minus e squared divided by 4 ln 2 to the squared plus e squared like this. And now my big question here, is this positive? And this, of course, is equivalent to asking if this thing here is positive. So let's investigate this briefly. So this then is the same as having, so if we only focus on this, then we can move this to the other side. So we have 4 ln 2 to the squared bigger than e squared. I'm only dealing with positive things here, so I can take the square root on both sides. So now I'm having this. And of course, this thing here is 2.718, something like this. And what is this? Well, if we use a calculator, we'll see that this is 2.88 something. So yes, this is bigger than this, not by much. And later in the course, this is something we can do by hand by using Taylor polynomials to figure out that this inequality here holds, okay? But right now, let's just accept using some type of calculator. And of course, this means that we've established that this thing here, this final question mark, is strictly bigger than 0. So this means that here we have exactly one solution. Here we have exactly one solution because we pass from negative to positive and we're continuous in between. And here we have exactly one solution. So we know that our equation, which we began with, which was this thing here, it has exactly 3 solutions. And one of these solutions is negative, the other is in this interval here, and the third is in this interval here somewhere. Let's even go to Python to visualize this to see if this makes sense. So let me first put in my function here. So it was x to the square minus 2 to the x divided by x to the square plus 2 to the x, like this. And let's put minus 10 to 10. And before I plot, let's put plt ytx at 0 like this. Let's also put some grid here. So now we see here. Here we have one solution, he's negative. Here we have one solution, so he is between 0 and 2.888. And if we remember, 2 divided by 2 was 2.888, and this is exactly the endpoints of the interval that we did detect one solution. And then the final solution is to the right of this, and by golly, he is here. So if I wanted to know more of where this 0 is, so I basically knew that we were positive here, and then we have, then we're heading to -1 here somewhere. And well, if I know, if I'm able to compute that at 5 I'm negative, then well, I know here I'm negative. I'm going to a negative asymptote, so here there are no zeros. And I know that I'm positive here and negative here, so in between here I have a 0. So in this sense, you can try to pinpoint the solution a bit more. And this is basically trying to pinpoint the solution in a better and better way by choosing smaller and smaller intervals where you can identify what happens at your endpoints. That's in fact the idea behind the so-called bisection method, which we will actually use to prove the intermediate value theorem that we've used here. So this is an idea that will play a part theoretically later in this course. And we're done.